of the snoofer workshop, and we've got a nice couple of talks. We've got Katie Schuman, and then a couple of talks on software stuff. So let's start off with Katie. Katie's currently a research scientist at Oak Ridge National Lab, but moving, I think, in January to University of Tennessee. So congratulations with the new job. And I believe from her Twitter is recruiting grad students at the moment. So do get in touch with her if you're interested in that. And yeah, I think I'll just let Katie speak for her stuff now. So yeah, go ahead.
Thank you. Thank you so much for the invitation to speak. So I'm going to be talking about evolutionary optimization for spiking neural networks and neuromorphic computing today. So just a little bit more background. I actually did my PhD at the University of Tennessee on evolutionary optimization of spiking neural networks. So I've been working on this for over a decade now. Since I've been at Oak Ridge, I've really focused on neuromorphic systems in particular, programming neuromorphic systems, again, using evolutionary optimization primarily, and just have been more broadly looking at neuromorphic computing from hardware, software co-design to applications, algorithms, and software for the last 6 years at Oak Ridge. I have a U.S. Department of Energy Early Career Award that's specifically focused on new training and learning approaches for spiking neural networks. And as Dan said, I am beginning as an assistant professor in the Department of Electrical Engineering and Computer Science at UT in 2022. None of the work that I've done has been in isolation. You can see all of the students and faculty who have worked with us over the last 6 years on this work. I will be citing various of them over the course of the presentation. If you're interested in joining us, please reach out to me if any of this resonates with you. So I'm going to be talking entirely in this presentation about evolutionary optimization for neuromorphic systems, or EONS, which is a tool that I started developing as a graduate student and have been refining over the last decade. So the way that EONS works is that it's going to be designing all aspects of a spiking neural network. Everything from the number of neurons and synapses to how they're connected to all of the parameters associated with them. And when I started developing this, as I started to even look at spiking neural networks as a neural network type, I was sort of thinking, okay, it's not clear to me that the right structure for a spiking neural network should be the sort of traditional layered structure that we might see in deep learning. What other structures might be good for it to use? And I didn't have a good intuition to develop about, okay, well, what's the right structure to use, even looking to neuroscience for inspiration for different applications and for particular neuromorphic hardware implementations. So that was sort of the impetus for developing EONS, was saying, okay, I want to come up with an algorithm that will just design it for me, assuming that I know nothing about what the spiking neural network should look like. So the way that this works is we start with a collection of randomly initialized spiking neural networks for a particular problem that we want to solve, and usually a particular neuromorphic hardware implementation, or at least a neuron model, synapse model simulation that we would be using for a spiking neural network. And here I'm showing 4 networks to start our population. Typically, our populations have 100 to 1,000 individuals. You can see that the networks have different numbers of neurons, different synaptic connectivity. The different colors are meant to illustrate different parameters. And then what we're going to do with these is evaluate and rank them. So typically, in the context of a neuromorphic application, we're going to take each of these networks, load it onto the neuromorphic hardware, or a simulation of the hardware, or a spiking neural network simulator, whatever, and then run it on the application to see how it performs. So the hardest part of using EONS is defining what that fitness function should look like. And I'll talk a lot more about that over the course of the presentation. But basically, that fitness function gives us a score for how well the network is performing on that particular task. And we take those scores and we rank the networks from best to worst. Now, at the beginning, when you start with these random initializations, they're all terrible, but some are less terrible than others. So we can establish this ranking. If you happen to know something about what the network should look like, you can embed that into your initial population. But usually we don't. We don't make any assumptions about what it should look like. And so we start from scratch each time. So once we have this ranking, we use a selection algorithm to preferentially select better performing networks to serve as parents while still maintaining some diversity We use tournament selection most typically, but you can implement a custom selection algorithm. We also support other selection algorithms from the genetic algorithm literature in how you want to select your parents from the population. We then perform reproduction operations. This is, if you'll forgive me, where the magic happens. This is where we get our children from the parents. The reproduction operations include just cloning a parent into a child, random mutations that add neurons, synapses, change the parameters within the network so it can make structural changes. It can also delete neurons and synapses. We also have crossover, which takes two parents and produces two children, which inherit characteristics from both of their parents. And we have an operation called merge, which takes two parents and creates a child that is the union of both of those parents in terms of structure. It has all of the structure of both of its parents, and then it inherits the parameters from each of the parents randomly. Once we have the child population, we repeat this process. That completes a single generation. We now go back on the child population. We evaluate and rank those, do selection, do reproduction, and so on. And we iterate until we reach a desired performance level. Now, if you know anything about evolutionary algorithms, you're already thinking, this is slow. It's going to take forever to be able to do anything with this. There's a reason that the acronym is EONs. It's not as bad as you might think, though. For a lot of the applications, in fact, all of the applications you're going to see on the rest of the presentation, we train in under 24 hours. You can do training on your laptop. You can also leverage whatever compute resources you happen to have. But there's a lot of reasons that we use evolution, and in particular EONs, particularly for spiking neural networks and for neuromorphic hardware more explicitly. And so I'm going to highlight those reasons now with some vignettes about some of our research. So the first and perhaps most important for our research is that it's applicable to a wide variety of tasks. It does not require that you change the underlying algorithm in order to adapt from something like classification to control to anomaly detection to whatever task you might want your network to perform, maybe even replicating some sort of biological behavior. So I'm going to give you some examples of some of the tasks that we use to evaluate EONs. This first one is a temporal scientific data classification task. In this case, we were looking at data from a neutrino scattering experiment called Minerva at Fermi National Accelerator Lab. This is another Department of Energy lab in the US. You can see a picture of the detector on the slide, a cartoon, obviously. There's a little cartoon person for scale. It's about the size of a school bus. And what happens in this detector is it's exposed to a neutrino beam. And all of the pixels along the detector are looking for certain types of events that are occurring within the detector. And the events that we were looking at here were when energy levels were going above a certain threshold. So already it's probably resonating with you that I said events. This translates very naturally into spikes that might be amenable for a spiking neural network application. The particular task that we were looking at was a classification task to look at this data and classify the horizontal region along the detector where the interaction originated. So at Oak Ridge, we actually took two different approaches to this task. We took a convolutional neural network approach and a spiking neural network approach. With the convolutional neural network approach, we were using also a genetic algorithm called Mendel to do neural architecture search and hyperparameter optimization to customize the structure for this task. So we were optimizing the network in the convolutional neural network as well as optimizing the spiking neural network structure. The differences in accuracies here are negligible. They basically get the same performance. But what you can see that's interesting about this, one, you can see the spiking neural network on the slide here. It looks kind of crazy like a hairball. Most of the networks that EONs evolves looks kind of crazy like a hairball. You can also see the convolutional neural network structure up across the top. You'll notice that it has a couple of fully connected layers at the end here. And one of those, this second fully connected layer, has 98 neurons in it. So just that layer has more neurons than our entire spiking neural network. You'll also notice that we are only using 86 synapses. It's not even fully connecting all of the neurons. We don't get rid of any of the inputs and outputs when we're pruning our network. So it's not actually using all of the input features to make a decision. Because we're using this structural evolution, that can actually tell us something about the problem space of what's useful and what's not for trying to solve our problem. So why is smaller interesting in this case? Well, energy usage is one factor for neuromorphic, obviously. We estimated that we could do this classification at about 1.66 microjoules per classification on a memoristive neuromorphic implementation. But when you're talking about a school bus-sized scientific detector, maybe you don't care about energy usage, but it's small, so it can also be fast. So that is very important for these sort of high energy physics experiments. So we certainly applied EONs to classification tasks like this one. But one of the most frequent classes of problems that we apply spiking neural networks and evolutionary optimization to are control problems. As you saw on the slide with all of our students, we work with a tremendous number of students, and in fact, a lot of undergraduates. The first thing that we make all of our undergraduates do is build an application to test with EONs and spiking neural networks. These are some of the applications that our undergraduates have built. Let's see if I can get the video to play. A lot of them are video games, perhaps unsurprisingly. In these cases, the fitness function that we're using for most of these, if it's a video game of some form, it's usually the score. We also have a couple of robotic navigation tasks where the score has to do with how quickly it can navigate towards a target or cover as much ground in the environment as possible. So we definitely use evolutionary optimization to evolve all sorts of networks. And it's worth noting for every single one of these networks that is playing each of these games or controlling the robots or whatever, all of these networks are under 100 neurons, under 200 synapses. So again, we're talking about very, very small networks that are solving these applications. So these are quite literally toy examples, but I have a couple of real world examples that I wanted to show you as well. So we've worked with researchers at Oak Ridge's National Transportation Research Center on applying spiking neural networks on neuromorphic systems for engine control for fuel efficiency. And so the idea here is you have an internal combustion engine, and at each engine cycle, fuel is being injected into that engine to keep it running. And so what happens is as you decrease the amount of fuel that you're injecting in the engine, you're more likely to cause partial burns and misfires, which can cause noise, vibration, and harshness in the operation of the engine, which is undesirable. And so you can't just keep decreasing the fuel because you're going to get those undesirable behaviors. So what we wanted to do in collaboration with these transportation researchers is come up with a spiking neural network that could take sensor data from the engine about what's going on inside the engine, in particular the amount of fuel, the amount of air, and the amount of inert gas within the engine at each cycle, and make a decision in real time about how much fuel to inject so that we can reduce the amount of fuel used while simultaneously meeting the acceptable performance metrics, which in this case was reducing the number of partial burns and misfires ideally to 0. So we developed a spiking neural networks using EONs. On the Summit supercomputer, we only used 24 nodes of the 27,000. We used those for 2 hours to evolve all of these networks, and we evolved a set of them that we could then evaluate. We trained them with a simulation of the engine, and then we deployed them to an FPGA-based neuromorphic implementation called MicroCaspian, which we could then run in the loop with the engine at the National Transportation Research Center. So in this case, the fitness function is adapted so that we're doing this sort of multi-objective optimization where we're simultaneously minimizing the fuel and minimizing the number of partial burns and misfires. If you're interested in the precise formulation of that function, you can check out the paper on this. So this was a pandemic project, so I asked them to take a video of what this looked like. This is the neuromorphic implementation that the spiking neural network is deployed on. It is interfacing with a host computer. You can tell that this is science because we're duct taping it together. This is the real-time information that we're receiving from the engine, and it's changing the fuel amount at each cycle. So the spiking neural network is running on that neuromorphic implementation with the engine in the loop, controlling the engine in real time. And it was actually able to translate what it learned in simulation into the physical engine, and the network outperformed the fixed control strategies on the physical engine as it did in simulation. So we're really excited about this. We're actually continuing this work to do real-time evolution with the engine in the loop, so continuous learning with the engine. So that is one example. And another example is yet another one of our pandemic projects. I really like to evaluate spiking neural networks on real-world problems. I like to have platforms that we can test them on. And one of the platforms that we are now testing with is this F1/10 platform. This is a 1/10 scale Formula One vehicle. There's a full community surrounding this. I encourage you to check it out if you would like to play with these vehicles. They have all of the specs for what you need to build them. Why is this interesting? For neuromorphic computing, this is a relatively inexpensive real-world demonstration of what neuromorphic computing can provide. And it is one step along the path of using neuromorphic systems for autonomous vehicles control. And it's one that I can play with at my house, which is also attractive for a pandemic. So what do? We did the same thing here that we did with the engine. We trained in simulation, and actually we trained on just a workstation and not on the supercomputer. What we're receiving to the spiking neural network is LiDAR sensors as input, and the output is steering angle and speed for the car. And we're taking our best evolved spiking neural network, we're deploying it to, again, the same FPGA-based neuromorphic platform, MicroCaspian. We're also simulating it on the CPU on the Jetson in lieu of not having the MicroCaspian. And so what does the training simulation look like? Well, it looks like this. The car is this little black dot. Hopefully you can see it going around the track. We actually trained on 1/10 scale Formula One tracks. I know nothing about Formula One, so this is Catalunya. We trained on five training tracks, and then we tested in simulation on a variety of other Formula One tracks that it had not seen over the course of training. But of course, it's really nice that we have the physical car, but we actually want to deploy it and test it in the real world, which means that you need a racetrack. So we built a racetrack in my basement where I'm sitting right now. So this is the first fitness function that we used in applying eons to this task was just drive and don't run into things. Complete as many laps as you possibly can. So you'll notice it's not quite acting like a race car yet. It's going pretty slow, because it didn't have speed as an objective. So I actually have a couple of high school students, they're seniors at Oak Ridge High School here in East Tennessee, who are working on me with this project. So they have been adapting the fitness function for eons to try to make it go fast. And this was actually a couple weekends ago, a new, faster network that is now driving the car successfully around these haphazard tracks that we've built based on cardboard boxes that we bought. So you'll notice it still has some undesired behaviors. This sort of weaving salmon-like behavior. We're working on the fitness function to adapt that so that it will also remove that behavior as part of the training process. And it's worth noting that all of these networks trained again in under 24 hours on a workstation. So those are a couple of the applications. All of those, the EONS algorithm, the way that the reproduction works, the selection works, all of that does not change. All we're changing is the fitness evaluation, and it is tailoring it to the particular application of interest. Okay, so why else do we use evolutionary optimization? So as I noted, it can learn the topology and the parameters and not just the synaptic weights. So this was really attractive for me because, again, I sort of had the intuition, whether that's correct or not, that these sort of layered structures may not be the best way to do spiking neural networks. And we wanted to be able to evolve the structure to see if it could discover what different structures might be able to solve problems. And so what do the networks look like? These are some simple classification tasks like iris and wine and breast cancer. The toy data sets that you might see, I just wanted to give you an example of those. Extremely small networks with few hidden neurons. EONS will evolve to try to use the input and output neurons for computation as well. We see a lot of recurrent connections, a lot of this hairball structure that's going on. As we saw in the Fermilab data, it will also evolve, to say some inputs aren't required, some outputs may not be required to solve the problem that you've selected. And so I didn't prune this network here, but you can see that some of the input neurons aren't connected at all, and some are just connected to themselves where it's not actually affecting the functionality of the network. So you could prune those out to get even smaller, and it tells you something about how to solve your problem. So what is the other attractive feature of using very small networks? Well, we can start to drill down into what they're actually doing and how they're making decisions. So I am far too impatient to do this, but my collaborator at University of Tennessee, Jim Plank, hates machine learning because he can't explain what's going on. So he really just wants to understand what's going on when EONS evolves a network. So he will drill down and actually look at what's going on in the network to try to explain what's happening. So this is a task front-facing sense and avoid. We have this agent, it's got the Mars coloration here in the middle, that's trying to navigate towards this purple column as the target, and then it's trying to avoid these meatballs along the way. And it has LiDAR sensors on the front, 25 as its front panel. That's its sensor information. Its inputs also include angle to the target, 2 altitude sensors for low and high, and a bias, which is like a heartbeat that's just giving it continuous input. Its outputs are go left, right, down, up, forward, backward, and then there are just 3 hidden neurons here. And so here is a video. Let me play the video of it in action, navigating throughout the environment, and you can see the activity in the network that's sort of aggregated across simulation runs to see how it's actually performing. So Jim traced through exactly what was going on and started to identify some things about these networks. So for example, one of the things that he saw is that the bias, that heartbeat neuron, is directly connected to go forward. So the default behavior in absence of everything else is just keep going, just keep swimming, just keep moving forward. As perhaps expected, we didn't embed this into the network, but it makes sense that it would evolve it. If the target is to the left, it connects to rotate left. Similarly, if the target is to the right, it connects to rotate right. But if you have conflicting goals, like the goal is to the left, but there's also trouble to the left, there are obstacles to the left, then the behavior here is to go left and go up, but also move back so that you're turning in the correct direction, but you're actually moving backwards. So when you have networks that are this small, you can start to trace into what they're doing. This is where I'm going to attempt to live demo because I wanted to show you another one of these networks and how we actually do this. So this is actually the network that was driving the car in the faster example. And so this is one of the simulators, and here it is. We've slowed down the simulator significantly so that you can see what's going on. We're actually currently in the process of tracing through what this network is doing. And our visualizer lets us look at the activity, see how it's actually driving the car in real time, and do things like drag different neurons around, organize them in different ways. The visualization also lets you label the different neurons so that you can try to understand what's going on with these. Because even though there's some complexity in this layout with lots of synapses connecting lots of different directions, it's still small enough that maybe we can wrap our brains around what's going on in it. Okay, so I'll stop those, go back into presentation mode. Hopefully you can see that again. Okay, so evolving the structure, the topology is also a big feature of this approach. Obviously, in the context of neuromorphic computing, having the ability to be applicable to different architectures and devices is really important. So EONs will attempt to tune directly to the underlying hardware. So just to give you some quick highlights on how we've applied this to neuromorphic systems. We've worked with EONs a lot for co-design to help us understand how to design the underlying hardware when we're working with emerging devices and materials. And so one of those is a collaboration with Garrett Rose's group at the University of Tennessee, looking at memristive mixed analog digital system, neuromorphic systems, where the synapses are implemented with hafnium oxide memristors. So in this case, we used EONs for co-design in simulation to understand the effects of this particular architectural layout and the hafnium oxide memristor on the plasticity mechanisms that we should realize for our applications, on the neuron and synapse models that we should use, and on the connectivity requirements that would then influence the actual chip tape out that we're in the process of doing now. Oops, sorry. Another architecture that we've worked with is by far the weirdest neuromorphic device I have worked with to date. This is a group at Oak Ridge's Center for Nanophase Material Science that decided that they wanted to build a neuromorphic synapse out of alomethicin-doped biomembranes. These are literally 2 water droplets encased in lipids that are squished together to form a membrane. Then you apply a voltage to one side and it opens an alomethicin channel ion movement. It acts like a chemical synapse. They're weird, and definitely weirder than every other device that I've worked with in neuromorphic systems. So again, we came up with a simulator for this device based on the experimental data. And we used eons to evolve networks that would solve real problems with these devices, trying to figure out how to leverage the inherent plasticity mechanisms of the biomembranes and how to design the corresponding neuron model to operate with those biomembrane synapses. And we actually designed it was a 6-neuron, 6-synapse network of these that would do EEG classification. So we're continuing to work on that as well. And we've also worked with researchers at NIST, led by Sonia Buckley, in looking at their single flux quantum-based neuromorphic system. In this case, they really wanted to use eons to come up with small networks that they could actually fabricate with their devices, because they couldn't fabricate even a network that would solve MNIST, because it was just too many devices for them to do at the scale of fabrication they could accomplish. So they still wanted to solve interesting tasks. So we used our eons approach to design networks that were small enough that they could actually fabricate them. We also used eons in this case to help them understand what the features of the neurons and the synapses they actually needed to solve these real-world applications, and tailored the design of the neuron model in these cases as well. So the same application in all three of these architectures will not result in the same spiking neural network. It will tailor the spiking neural network. Eons will tailor the spiking neural network to the underlying hardware to try to leverage whatever the characteristics of the hardware are to try to solve that problem. Now, at the same time as it's going to try to leverage the characteristics, it can also operate within the constraints of the architecture of the device. And so we do evolve under hardware constraints depending on what the actual constraints of the hardware are. So if you happen to have limited weight precision, limited delay values, structural constraints in the physical network connectivity you can realize, eons will optimize within those constraints. And in this chart, I'm showing different constraints on delays and weight values, and the accuracy ranges here just under 90% up to about 92.5. And you can see it was able to tailor the network depending on whatever those constraints were to still perform pretty well. So pretty much everything that I've showed you already, we're using eons to evolve the structure of the network as well as the parameters, but we can actually combine eons with other training and learning approaches to be able to learn other aspects of the network, or have eons only learn, for example, structure, or only learn parameters. So we have combined it with liquid state machine or reservoir computing-like approaches, where we were asking the question, how do you decide what the reservoir should look like? We actually had a graduate student who worked on this. And in this case, we were looking at eons designing the reservoir, but the readout layer is still trained as normal. And we found that, perhaps unsurprisingly, even when you're trying to encode in your random reservoir generation the rules that we know about how reservoirs ought to work, having eons evolve the network can give you better results by doing this. I also had a graduate student who worked on combining eons with STDP. And what we found in doing this is combining STDP and evolutionary optimization. And in this case, we were using just an unsupervised STDP learning rule. It resulted in better generalization in smaller networks than the individual algorithms by themselves. We actually also wrap our eons and STDP, as well as eons by itself and STDP by itself, with a Bayesian hyperparameter optimization approach, which tunes the hyperparameters of everything. It tunes the hyperparameters of eons. It tunes the input encoding approaches that are used. It can tune hardware parameters as well as STDP parameters. And so we're trying to make a sort of one workflow that will allow you to play with different algorithm combinations and tune it for you automatically rather than you having to do it manually. We've also used eons to evolve ensembles of spiking neural networks, and we've shown that our ensemble approaches outperforms the evolution of a single network for classification tasks. The best performing ensemble evolution approach was a diversity-aware ensemble evolution. In this case, each of the networks that was evolved in the ensemble knew what the other networks were learning, and that influenced the evolution of the ensemble collectively. So we were trying to improve the performance, the diversity of the networks to give us the most accurate performance. And if you're interested in learning more about that, there's a paper on that as well. So I hinted at this earlier in talking about the applications. In defining what the fitness function looks like, we're often doing some sort of multi-objective optimization. In the case of the engine example, we were looking at minimizing the number of partial burns and misfires while simultaneously minimizing the fuel, which are trade-offs on each other. In the car, we want to go fast, but also not crash into things. So we have these sort of multiple objectives just in the performance on the application. But often we also have other characteristics that we want to do multi-objective optimization with, such as minimizing the energy usage of the network on a neuromorphic hardware implementation, minimizing the network size, or improving the resilience. So you can update the fitness function to encourage different properties of the network. In the slide here, I'm showing the testing accuracy, the number of neurons, and the number of synapses with no multi-objective shown in blue, and multi-objective optimization to minimize network size shown in orange. And you can see that by adding this additional objective, we're not impacting the accuracy at all or very little, and we're significantly decreasing the size of the networks. We've also done multi-objective optimization for resiliency, and in particular, as you probably know, in dealing with neuromorphic systems that have emerging device types, those devices often have faults or failures or noise associated with them. So we want to be able to continue to operate normally, even in the presence of those issues. So we can update our fitness function to include not just the score on the original task, but also the score in the presence of different types of failures, in this case, small perturbation to the weight values on the network. And when we're doing this, we can then evolve for resiliency as one of our objectives. In this case, we're also evolving to decrease the network size. So trying to minimize the network size, trying to improve the resiliency, and optimizing for performance on the task all simultaneously. And with that particular optimization approach, we were able to show that we could significantly improve the resiliency of the network in the presence of those weight variations. And this was on a pole balancing task. Similarly, if our failures are even more extreme, in this work, the failures were complete synapse failures. The synapse just stops working altogether. We adapted the fitness function in a very similar way, where we had a weighting factor for how important the original accuracy is versus the accuracy on networks with imposed failures. And we found that as we decrease the importance of the accuracy on the original network, we could see improved resiliency. And these are the resiliency curves. So the testing accuracy in the presence of 10%, 20%, 30%, 40%, et cetera, of the synapses deleted on a couple of different applications. So we still achieve comparable performance in terms of accuracy on the original network, but also improve the resiliency of the system. Okay, so it's slow, right? They can be slow to converge.
Katie, can I just briefly interrupt to say we're a little bit over time, so if you could try and...
I'm so sorry. Yes, I will wrap up very quickly.
Okay,
if you happen to have a supercomputer, which we do at Oak Ridge National Lab, but if you happen to have a cluster or cloud or access or whatever, we can scale up on high-performance computing systems. We use an island model where we run populations individually, and they share information via migrants. So individuals migrate from one population to another. By doing this, we can significantly improve computation, get to better results faster with more resources. So again, if you happen to have a supercomputer, you can use it. If you happen to have neuromorphic hardware, you can also use it to get to better performance faster. You can either use it as an accelerator or to get lower power performance. And in this case, we did neuromorphic acceleration using a Xilinx Zinc system, which is an FPGA-based implementation. And we're able to show that we could get comparable timing performance, actually a little bit faster than what you would see on a laptop with significantly less power. So there's a lot of reasons that we use evolutionary optimization. There's a lot of ongoing work that we're doing. We're evaluating the performance of different neuron and synapse models as you add biological complexity and plausibility into the models. What effect does that have on real-world application performance? Evolving structures of simple neural components to form more complex neural behaviors, trying to match, again, biological behavior. We're evolving synaptic plasticity mechanisms. We're combining with a variety of different neuromorphic algorithms, and we're exploring indirect encoding approaches for scaling the spiky neural network size. So even though evolution can be slow to converge, it has a lot of attractive qualities for spiky neural networks and neuromorphic systems. There's a lot of opportunity to combine it with other spiky neural network algorithms. And I think it's exciting that we can use it to probe into the computational capabilities of spiky neural networks and neuromorphic computers more broadly. And with that, I will thank my collaborators at Oak Ridge and at the TinLab Neuromorphic Computing Research Group, and I'm happy to take your questions.
That was brilliant, Katie. Thank you so much. That was really inspiring talk. Really impressive array of work. Thank you so much. We've got tons of questions. The first one, the top voted one, was actually my question, which you pretty much answered, but I'll do a slight variation on it. So my question was, could you alternate evolution steps with gradient-based steps? And you definitely answered that. You definitely can do that sort of thing.
100%, yeah.
Can it speed it up?
Yeah, so by doing that, you can definitely speed up the parameter optimization, because when you're optimizing all of the parameters, especially as your network scales up, that gets to be rather large. That's why we're exploring these indirect encodings. But using the evolution to tailor the structure along the way, you can restrict it to be a structure that a gradient-based approach can handle. EON supports that. And then you have that to be able to tailor the parameters along the way. So yes, it can definitely speed it up.
Cool. So the next question, it's a slightly different sort of style of question. Basically, the question, as I understand it, is asking, can you use this evolutionary approach to sort of learn what the plasticity mechanism should be? Basically, they're saying, we know the ingredients, you've got your pre and post traces, you've got all of these sorts of things. Can we use evolution to work out what the plasticity rule should be?
We're doing this right now, and actually, I would like to reach out to Enrique as well after this is. I'm actively working on this, and so we've done it already in the context of sort of a limited, assuming a sort of STDP-like structure, and we're just optimizing the parameters for a particular application. But we're actually using genetic programming now, along with EONs, to optimize the entire formulation of the plasticity mechanism, taking the spike trains, the pre and the post, as input to be able to optimize what the plasticity rule should even look like. And we're going to actually interleave the evolution of the structure alongside the plasticity to try to evolve structures that learn well with that particular plasticity rule.
Okay. Is there a relation there with, I know that Tim Vogels was looking at trying to find what the optimal plasticity rule should be using backprop. Is there any relation with that?
We haven't done anything with backprop with the optimal plasticity rule, but I imagine that there is going to be synergies with that. Okay,
yeah. Cool. Okay, so the next one is there an argument, either mathematical or philosophical, saying why it should be possible to reach the optimum architecture using your sort of genetic approach, I guess?
That would be a more genetic algorithm literature question. There's a lot of literature in the genetic algorithm space, but I think for me, what's interesting about the evolution approach is that we can evolve for the same task. Each evolution run might result in a completely different structure. And so I don't know, even for spiking neural networks, there isn't one best solution, I think. That you may have for this sort of Pareto optimal, depending on what your performance characteristics are. Like, do you care most about accuracy? Do you care most about energy? Do you care most about runtime? Defining what the optimal is already a question. But convergence rates and things like that's left to the genetic algorithm literature. Yes, it should be able to eventually evolve, just given enough time.
Okay, yeah. So I think Friedemann is asking, what's your input encoding in your systems, and do you also evolve that?
Yes, we evolve that. So we have a software framework that we use, and we support population coding, rate encoding, temporal coding, stochastic rate encoding, a variety of input encoding procedures. We can optimize it as part of the EONs process, but we can also do that hyperparameter optimization where we're optimizing the input coding as part of that.
Cool. I'm just going to quickly inject my own question, which I didn't get to ask here. So you said that the robot car thing was inexpensive. Roughly how much does that cost actually to set up?
That particular platform is about $1,000, but there are cheaper ones. There's one that's about $250, so we're going to be buying a couple of those too. But yeah, cheap, LiDAR input. They have lots of simulators, lots of software, everything you need to get up and running on that. I would love for that to be a benchmark for the neuromorphic community to target for neuromorphic hardware.
Yeah, no, I'm just thinking about it because I'm going to start a spiking neural network course at my university, and I'm wondering if it's something I can get for the students.
Students love this. Everybody loves it, actually. It piques the interest of every researcher that comes.
Well, the videos were cool. Whether or not we find enough space in London to set something up like that is another question.
Hey, I did it in my basement. That's so do it anywhere.
Cool. All right. So the next question: did you consider different types of random initializations for the connectivity, and did it change the convergence rates?
That's something we're working on right now. So we just injected a bunch of all the results that you saw were just on uniform random initialization. There was nothing special about the connectivity. We have now implemented different random network initializations, small world, a variety of others that are now escaping me. But yes, we will then. We're evaluating that now. That is an ongoing study.
Cool. And then the next one is, I think maybe you've already answered it, but they're asking, have you tried transfer learning, i.e. using something you've optimized for one task as part of the initial pool? And I think that's kind of what you were doing with your sim to real, right? So
right, but we really want to establish a library of useful networks that you can draw from to initialize your population in a sort of transfer learning way. That is also something that's ongoing because it's not clear to me how well things would translate from, for example, the engine to the car. Is there something useful that's going on in the engine application that maybe a sub-network that would also be useful in the car scenario? Maybe there is, maybe there's not. But that's something we do want to explore.
Cool. So actually that relates to a question someone else asked about. So Carl Johnson asked, which is, do you have a way of preserving and passing down submodules within a network to children? I guess that's
we're working on that. That's active work. It's something I've wanted to do from my dissertation days, and we are now working with like graph theorists and things like that to help us identify what those submodules should be.
Okay, cool. Yeah. So the next question is another one of mine. Which was, did you think about running your evolutionary algorithm not directly on the network, but on a sort of network growth rule?
That's what I mean by the indirect encoding, and I think somebody asked in that. Yeah, so the indirect encoding is basically you're not representing every individual component, neuron, synapse, weights, et cetera, connectivity. It's more like a growth rule that you would evolve the way that the network grows rather than every individual aspect of the structure. We're working on that right now with some genetic algorithm experts. Okay.
So are you thinking about that more in a sort of graph theory way, or are you thinking about it in terms of like how biological growth rules work, with like gradients?
We're thinking about it more in a graph theory way, but that's because we don't have the expertise. So if anybody has that expertise on the biological growth rules, network growth rules, I would love to incorporate that into the way that this could evolve, those sorts of growing and growing rules, neuron growth, neuron deletion over the course of evolution. I would love to do that.
Yeah, there are a couple of recent papers about that might be interesting. There's this idea of the genomic bottleneck that might be worth looking up. Yeah. Cool. Let's see what's next. So Carlos asks another question. Have you considered the evolving evolvability phenomenon, learning network architectures that are most modular and adaptable to new tasks?
Yes. So this is having a learning rule embedded to learn a structure that is most useful for that particular learning methodology or algorithm or whatever, that could be applicable across multiple tasks. That's something that we're doing when we're evolving the plasticity and structure simultaneously, is we want to make sure that it's not just targeting it towards one particular application, but something that would be useful across multiple applications.
Yeah, and the last question actually is a bit related. Have you observed any patterns across different tasks regarding what are the best connectivities?
It's really hard to analyze. That's why we've got the graph theorists. It's not even clear. It's the graph isomorphism problem of like, how do you identify that it's the same from network to network? So we're actually, we just did a proposal this morning, pitch on looking at graph embeddings to analyze the network structures to see if that will help us analyze the structures more effectively. Cool.
Okay, well, excellent, brilliant talk. I think we've got to move on to the next speaker. But yeah, that was brilliant. Very, very inspiring indeed. I'm sure you'll get lots of PhD applicants after that.
Please reach out to me. I left my email up the whole time for that reason. Thank
Brilliant.
you.
Cool. All right. Thank you so much.
Thank you.
And I think we might need to both close our window to stop the thing because, yeah, let's see if that